Even after finding the potential of a single homoid, the integration of all the shells to describe a physical system still results in cumbersome integrals. I'm going to quote here the potential for a homogeneous ellipsoid, which is given by this expression, where I, A1, and A3 are dimensionless coefficients. R is the radial coordinate, Z is the vertical coordinate, and A is the semi-major axis of the ellipsoid. This table here, which is from Binet and Trimay Galactic Dynamics book, lists the coefficients A, 1, A3, and I for oblate, prolate, and the triaxial cases. It cites here also A2 because actually this expression is for x and y, so it would be A1 times x squared plus A2 times y squared plus A3 z squared. But for our case of interest, the oblate spheroid, we would have A2 being equal to A1, and also for the prolate, when the two axes are equal, A2 is equal to A1. It's only for the triaxial spheroid that you need A2. And as you can see here, the expression for the triaxial is horrible. We are interested in the oblate, so the coefficients are a little bit more treatable. Our case of interest then is the oblate spheroid, which is the ellipsoid with equal axes in x and y, and they are both bigger than the short axis C, the vertical axis. So in this case, you have this coefficient, say 1 equal to 2, given by this expression in the table, and the I coefficient also given by this one, where E is the eccentricity, given by the ratio of the axis. And these expressions, they give the potential of a spheroid of any eccentricity between 0 and 1. Let's see if they make sense. Let's find the limits. Let's first get to the spherical limit. So at the spherical limit, the eccentricity is much, much less than 1. Also, these expressions here, they have R cosine. We can expand the R cosine in Taylor series. Let's keep to the second term, which is a cube over 6. And with these expressions, then, we have that A1 is equal to A2 equal to A3, which is equal to 2/3. And I here is going to cancel to be equal to 2. So substituting these values of A1, and A3, and I in the potential, this is what you get. Now, we should recover the spherical potential in this case. For that, then let's substitute R equals Z equal A equal to little r. And then I'll refine this. Indeed, if I now replace the density by the mass, we did find this as expected, the spherical potential. Let's also find the disk limit. The disk limit will be found by setting the eccentricity equal to 1, so that the arc sine here would be equal to pi over 2. Now the second term here for equal 1 is going to be finite, whereas this one is going to be much, much bigger. So this one will cut to this term, and then you have A3 equal 2. The same thing will happen for A1. And you can see that I is going to be 0, because E here is equal to 0, because this term here cancels. So these are the coefficients. A1 equal I equals 0, and A3 equal 2. So back in the potential, this is the potential for a very flattened distribution, for a very flattened spheroid, almost like a disk. And this is identical to the potential that we found for the thick disk inside the disk. So let's see how this solution goes from a spherical to a flattened distribution. Basically, what is happening to these coefficients as we flatten the distribution. So in the x-axis here, you have the eccentricity, and in the y here, the value of the coefficients, A1, A3, and I. So the blue curve here is A1, the yellow curve is A3, and the green one is I. What you're seeing here is A1, which is multiplying the radius, is starting as 2/3, just like the same coefficient for A3, if the distribution is spherical. As you flatten the distribution, as the eccentricity goes to 1, the potential due to radius goes almost to 0. And when the eccentricity reaches 1, it is 0. So the coefficient that is multiplying the radial distribution in the potential is equal to 0. And then the potential is given only by the Z distribution. Remember that I said that in the Poisson equation, if you have a very flattened system, is the Z variation that matters. The radial variation starts to not matter anymore. So this shows this behavior. A3 here is the coefficient that is multiplying the variation in Z. And A1 is the one that is multiplying the variation in radius. The importance of the variation in radius starts to decrease as you flatten the system, and the Z component is the one that ends up dominating.